Okay, good. Section 12.2, vectors. So in this section, we're just going to be defining intuitively what we mean by a vector. We will be in the next sections giving you a mathematical definition of vector, but this will more or less be the idea that of a vector that you get from, say, a course in physics or something. Okay, so section 12.2, vectors. So a non-mathematical description of a vector. So a vector has a length and a direction. So this little pointer here, having a length and a direction, is called a vector. So we start at this initial point and we go to some terminal point, and we will denote a vector, I guess, with a little arrow on top. Vector u is equal to the vector v if u and v have the same direction and the same length. I will denote by 0 with the little arrow the vector with length 0. So it doesn't really have a direction, but it has a length, and the length of it will be a length of 0. Let's define some operations on these vectors. And so first concept that I'll talk about is vector addition. And so let u and v be vectors. Reposition u and v so that the initial point of v is at the terminal point of u. Then the sum u plus v is the vector from the initial point of u to the terminal point of v. So diagram, we can think of this visually as follows. So I have here a vector u and a vector v. Then starting at the initial point for u, we have the initial point of the vector u plus v. And then the terminal point of u plus v will be the terminal point of v if we positioned v to have its initial point the same as the terminal point of u. This we call the triangle law because it looks like a triangle. Or similarly, we could have the parallelogram law. So I take the vector u and the vector v, having them both at the same initial point. I then place the vector v so that its initial point is the same as the terminal point of u. Then I take the vector u and position it so its initial point is the same as the terminal point of v. Then if I take the vector starting with the initial point, the same as the initial points of u and v, and the terminal points, the same as the terminal points of these moved, repositioned u and v, then this vector is the vector u plus v. And that's called the parallelogram law. You can do either way. You can think of the sum as either way. So that gives you a concept of the sum of two vectors. Next, let me give you the second concept, the second algebraic concept for vectors, the idea of a scalar multiplication. So let u be a vector, and let c be a member of the scalar field. So it could be any sort of field. If you don't remember what a field is, in the next section I'll give you a mathematical definition of a field. But it's really just basically the rational numbers. Whatever you can do with the rational numbers, that's the idea of a field. So in particular, in most of our cases, at least initially, we'll be looking at the real numbers. And so a scalar will be just some real number. So then the scalar multiplication, cu, is the vector of length c absolute value of c actually, times the length of the vector u in the direction of the vector u when c is greater than 0, and in the opposite direction of the vector u when c is negative. And so if c is positive, then, so suppose that this is the vector u, then c, u, will be a vector in the same direction or opposite direction. In the same direction, assuming c here is positive, as u, and it just lengthens or compresses the vector u. So if c is greater than 1, then cu will be some vector that's c times longer than the vector u. If c is less than 1, then it'll be c times shorter than the vector u. And of course, if c is negative, then it'll be the same thing but in the opposite direction. Okay, so let me look at components of the vector. So suppose I have a two-dimensional vector, let's say a. I will denote the fact that this is a vector by using these sort of weird sort of brackets. Okay, and so suppose that the vector is at the point, well, suppose that we've positioned the vector to start at the origin, and that it ends at coordinates a1, a2, then the vector a may be represented by a1 comma a2. If I, let's put this in black. I can also write this vector in terms of the standard basis. So I is a unit vector in the direction of the x-axis. J is a unit vector in the direction of the y-axis. Then I can write the vector A as A1 times I plus A2 times J. Now, of course, if it's a three-dimensional vector, then the components will be, say, I don't know, A1, A2, and A3, which I could write as A1I plus A2J plus A3K, where K is the unit vector in the direction of J. So, given the points A, with components x1, y1, z1, and B with the at the point x2, y2, z2, then the vector A, which is just the vector from the point A to the point B, can be represented as the vector x2 minus x1, so the difference of the x components from x2 minus x1, y2 minus y1, and z2 minus z1. Another important concept that we'll be looking at is the idea of length. And so the idea of length is, well, an idea of that we call magnitude, or mathematically we call it the norm. So the norm of a vector A, so suppose A is in two dimensions and it's represented by the vector A1, A2, then the length, the norm, the magnitude of the vector A is just the square root of the sum of the components of A. So A1 squared plus A2 squared. So in particular, if you have a vector in 3 dimensions, say that A is A1 comma A2 comma A3, then the length of the vector A is just the square root of A1 squared plus A2 squared plus A3 squared. So, in particular, let me look at what vector addition and scalar multiplication looks like for vectors in R2. So, suppose that the vector A is the vector A1 comma A2 and the vector B is the vector B1 comma B2. Then the vector A plus B has the following components: A1 plus A2 comma B1 plus B2. And suppose C is some real number, some member of your scalar field. Then the vector CA has components CA1 comma CA2. Now, you can do the same thing for a three-dimensional vector. So suppose that A has components A1, comma A2, comma A3, and the vector B has components B1, comma B2, comma B3. Then the vector A plus B has components A1 plus B1, comma A2 plus B2, comma A3 plus B3. We can define scalar multiplication as follows. So let C be any member of your scalar field. So the vector CA has components CA1, comma, CA2, comma, CA3. So let me give you the field properties. And so this will tell you what properties the scalars must satisfy in order for them to be, well, a member of their scalar field. They have to be a field. So a field will consist of a set, I'll call it F, along with some binary operations. I'll call it plus and minus. So plus will take the Cartesian product of F with itself to the field F. And so will the multiplication operation. It will take the Cartesian product of F cross F into F. We have a unary operation of negation and of multiplicative inverse. We have the nullary operations of, well, 0 and 1. So I have the closure property for addition, which is really just saying that this is a binary operation. So if I have any scalars A and B, then A plus B is still in. So if A is in the field and B is in the field, then their sum, A plus B, is also in the field. Okay, I went blank for I'm still blank for a second. Okay, sorry about that. Now, stop going blank. Multiplication is also a binary operation. And so if A is any member of your field and B is any member of your field F, then A times B is also a member of your field. We have, so that's the closure property for multiplication. If I have any members of your field A, B, and C, then I have the associative property. A plus the sum of B and C is equal to the sum of A and B plus C. And I also have the associative property for multiplication. A times the product of A and C is equal to the product of A and B times C. In addition to that, I have the commutative property of addition. A plus B is equal to B plus A, and the commutative property of multiplication, that A times B is equal to B times A. I also have, well, the existence here, this nullary operation. I have that there exists some number F in your field such that for any A in your field, A plus 0 is A. And so 0 here is a additive identity. It's the additive unit. And in this case, it's a right additive identity. But by the commutative property for addition, it's also a left additive identity. There also exists a additive multiplicative identity. So there exists number 1 in your field, such that for every A in your field, A times the multiplicative identity is the same value, A. And by the multiplicative, the commutative property for multiplication, we have that it's also a left multiplicative identity. Let me assume that the additive identity is not the same as the multiplicative identity. Otherwise, your field will be very small. It'll only involve the number 0. So let's try to make an assumption so that our fields have more than one member. Next, for every A in my field, for every number in my field A, for every number A in my field, there exists another number, negative A. So this is a unary operator. It acts on every number in the field. And it's such that any number plus its additive inverse is the additive identity. And so this is a right additive inverse. And by the commutative property for addition, we have it's also a left additive identity. Next, suppose that A is any non-zero member of your field. Then, again, there's this unary operator, the multiplicative inverse, the reciprocal. I'll denote the multiplicative inverse as A to the negative 1. And it's a member of your field such that any number times its multiplicative inverse is the multiplicative identity. And so this is a right multiplicative inverse by the commutative property for multiplication. It's also a left multiplicative inverse. And lastly, multiplication distributes over addition. So I have the distributive property. A times the sum of B and C is the sum of A times B plus A times C. And so that is, well, the definition of a field. And so a scalar is a member of, well, it's scalar field. And so a scalar is a member of a field. A vector is a member of a vector space. Let me tell you what a vector space is. So for vector space, let's say I have some set V. So a vector space is a set V along with some binary operations, vector addition, scalar multiplication. There is a nullary operation giving me 0, the 0 vector. Oh, maybe I should put a 0 vector here. And the negation, a unary operation of negation of a vector. And this will be over some field, which we gave you from before. This will be called the scalar field. This is the a member of this field will be called a scalar. So, just like before, we have the closure property for vector addition. So if U and V are members of this set V, then U plus V is a member of the set V. So if you add two vectors, you still are in your that are in some particular set. When you add them, they're still in that set. They don't, go out of that set. Okay. Next, these vectors satisfy the commutative property of vector addition. So U plus V is equal to V plus U. They also satisfy the associative property for vector addition. So U plus the sum of V plus W is equal to the sum of U and V plus W. Next, there exists, well, I have this unary nullary operator that takes, well, nothing and gives you a member of the um, vector space. So there exists some vector 0, a member of vector space, such that for any vector u plus this additive identity, you get back the same vector u. And so this 0 here is a right additive identity. By the commutative property for vector addition, you have it's also left additive identity. Next, we have this unary operation such that for every vector u in your vector space, I have a vector negative u such that any vector plus its additive inverse gives me the additive identity. And so a vector plus its negative vector gives me the 0 vector. Again, by the commutative property for vector addition, we get that not only is this a right additive inverse, it's also left additive inverse. So now some properties for scalar multiplication. Well, again, I have the closure property for scalar multiplication. If C is any member of your scalar field and U is any member of your vector space, then the scalar multiplication of C, of the scalar C, with the vector U is just some vector in the same vector space, V, in the same set V. Next, I have that scalar multiplication distributes over vector addition. So the scalar C times the sum of the vectors U and V is just the sum of the vectors CU with CV. Next, the scalar multiplication distributes over scalar addition. And so adding the scalars C plus D and multiplying them by the vector U gives me the sum of the vectors CU and the vector DU. Next, I also have that scalar multiplication. Well, let's say it this way, that scalar multiplication doesn't distribute, is associative with multiplication within the scalar field. And so if I have scalar C and D and vector U, then C times D, so the multiplication of these two scalars, times the vector u is the same as the scalar multiplication of c times the vector du. And lastly, the multiplicative identity of the scalar field is the scalar multiplicative identity. So the multiplicative identity for the scalar field, 1, times the vector u, is just equal to the vector u. Okay, so slight terminology. I don't know if I'll use this or not. I may have to use this in the latter part of the course. If F is not a field, but what's something called a ring, meaning that, well, we'll have to loosen the definition so that it doesn't necessarily have multiplication of these of these scalars. So if F is a ring and with identity, then well, it's not. Let me just say that it's not commutative, the multiplication. Then V is called a F module. So instead of calling it a vector space, you'll call it a module if rather than the scalars being a member of a field, they're a member of a ring. So the typical sort of object that's a ring would be matrices are rings. And so sort of if you know anything about what a matrix is, and we'll have to actually do things involving matrices in the near future, then that sort of idea that you can't multiply, any matrix times another matrix gives us that's sort of the essence of what a ring is. Okay, so I sort of said this from before. The standard basis. So let me give you the notation for the standard basis vectors. Okay, oh, and I guess I should write them sort of as a vector. So wait a second, let me put little vectors here. Okay, so if I'm just talking about two dimensions, then the standard basis for R2 will just be I, which is the vector having components 1, 0, and J, which will have the vector J, which will have components 0, 1. In R3, I will have components 1, 0, 0. J will have components 0, 1, 0. K will have components 0, 0, 1. So I is the unit vector in the direction of X. J is a unit vector in the direction of Y. And K here is a unit vector in the direction of Z. So, as I said before, you can write a vector A in terms of its components as, well, A1I plus A2J, or if you have three components, A1I plus A2J plus A3K. So I've been sort of saying this, but maybe I should actually write it down. So a unit vector in the same direction as the vector u is a vector of the form, well, the vector u divided by the norm of the vector. So let me do some examples on page 845. In problems 15 through 18, find the sum of the given vectors and illustrate this geometrically. Okay, so let's try to do that. So let's find the sum of these vectors. And so this is equal to the vector, well, just add 1 plus 0, 1, 3 plus 0, 3, 6 minus 2, 4. So this is the vector 1, 3, 4. Okay, so let me try to illustrate this, if I can, as best I can. So this is x, y, z. Okay, so I have the vector 1, 3, 3, negative 2. No, negative 1, negative 2. So this is, and maybe I'll do green. So this is my vector. It's hard to tell, but it's going down. It's supposed to be going downwards. So it's not, so it's going into the this tablet here. Okay, next, maybe I'll do purple. Oh well, let me do. And so this is the point 006. So 1, 2, 5, 6. Okay, so that's this vector. But so I have to do parallel. So this is 6. Okay. Yeah, that's pretty good. Okay, so there. So what I've done here is I've taken this vector here and moved it from here, this position to this position. Okay. And now let us illustrate. So I guess I should, well, I didn't call these anything yet. So now I have this vector going from here to here, and that's the sum. So this was the vector 1, 3, negative 2. This was the vector in purple. Was the vector, if I can, oh good, it's changed. Okay, it just blanked out on me for 1 second. This was the vector 006. Stop blinking out on me. It was the vector 006, which I transported, parallel transported, here to make it look nicer. And then this is the vector 1, 3, 4. Okay. Okay, so that's how I added these together. Okay, so let's see. 23 to, okay, so in exercises 23 through 25, find a unit vector that has the same direction as the given vector. Okay, so I have the vector u, which has components 8, oops, I plus minus j plus 4k. So let's find the length of this vector. It might be better to find the square of the length. So this is 8 squared plus negative 1 squared plus 4 squared. So this is 64 plus 1 plus 16, which is 81. And so the length of this vector, the norm of the vector, is just the square root of 81, which is 9. Therefore, the unit vector in the same direction as the vector u will be the vector, well, let's see, divide by 9. So it's 8 over 9 I plus negative 1 over 9 j plus 4 over 9 k. So this is a vector in the same direction, but it's a unit vector. Okay, so let's do problem number 37. A block and tackle pulley hoist is suspended in a warehouse by ropes of length 2 meters and 3 meters. The hoist weighs 350 newtons. The ropes fastened at different heights make angles of 50 degrees and 38 degrees with the horizontal. Find the tension in each rope and the magnitude of each tension. Okay, so I have here the following. So this has length 2 meters, and the angle here is 50 degrees. This is 3 meters. Angle is 38. And this has a downward force of 350 newtons. So let me draw this, redraw this sort of better. And so let's say it's here. So this is an angle of 38 degrees. It's an angle of 50 degrees. Let's call this T1 as the length of this vector, and T2, the tension, is the length of this vector. So I have a weight here, and it's going to be going down, has a force of 350 newtons. And so these have to balance out, so it's got to have a force in this direction equal to a force in the other direction so that they cancel out. Well, this has length t, so let me, T2, so let me do this. Okay, so if this angle is 38, this angle also is 38 degrees. If the length of this is T2, then the length of this is T2 cosine 38 degrees. And the length of this is T2 sine of 38 degrees. Okay. Let's do the same thing for the other side. So the length of this is T1, and suppose it looks something like this. So if this is 50 degrees, well, this has got to be 50 degrees also. These are parallel. And so this length here has got to be T1 cosine of 50 degrees. And this has got to be T2 sine of 50 degrees. Let's make that 5 look a little nicer. So 50 degrees. Okay, so for this vector T1, well, it has, well, let's see, this component is going up in the j direction, and this component is going in the opposite direction of the unit vector I. So maybe I'll put a little diagram here. This is the positive I direction, and this is the positive j direction. Okay. So This is going in the opposite direction here. So this should be a minus T1 cosine 50 degrees times I plus, so this other component of the vector, which is, it's going in the same direction as J, so it's T1 sine 50 degrees J. Okay, so let's look at this vector here, T2. So T2, well, this goes in the same direction as I, so it's T2 cosine 38 degrees I plus, well, this goes in the same direction as J, T2 sine of 38 degrees J. Okay. I have that, well, the sum of the forces must be 0. And so I have to have that T1 plus T2 plus this, which is a negative 350, and it's going in the negative J direction. These must all add up to be 0. So I have that T1 plus T2 is equal to, come on, what are you doing? Is equal to 350 J. Okay, so, well, that means that the sum of the I coordinates must be 0. So that's, well, and so I have T1, so it's a negative T1 cosine 50 degrees plus T2 cosine 38 degrees I plus, well, again, the J component of T1 sine 50 plus T2 sine 38 degrees J must equal 350J. So from this, I'm going to get two equations. Maybe I'll call my first equation R1. I might need that notation in the future, so I'll call it R1. So I have T2 cosine theta cosine of 38 plus T1 cosine theta, cosine of 50 degrees. So the I component is 0. So that's the first one. And let's do R2. So that's, call it T2 first. So T2 sine of 38 degrees plus T1 sine of 50 degrees. So in the J component, I have that's equal to 350. So if I multiply R1 times sine, so sine 50 degrees times R1 and I'm going to add because I'll give you a nice thing. So multiply by cosine of 50 degrees times R2. Okay, so let's do this. So I have T1, T2 okay. Oh, let's say cosine 38 degrees, sine 50 degrees. But then I'll get a T1 cosine 50 sine 50 equals 0. Okay, and so I'm adding to this. So that's equal to, since you get a 0 here, 350. Oh, wait, what am I? Let's minus T1. Wait 1 second. I was doing something in my head. Minus T1. Maybe I'll call it cosine 50 sine 50 0. And for this one, I get T2 sine of 38 degrees cosine of 50 degrees plus T1 cosine 50 degrees sine 50 degrees. Oh, come on. Cosine 50 degrees sine 50 degrees equal to 350 cosine 50 degrees. So let's add these. So these will cancel, and you get T2 cosine 38 degrees sine 50 degrees plus sine 38 degrees cosine 50 degrees is equal to 350 cosine of 50 degrees. Well, this is just the sum of, this will just be the sine of the sum of 38 and 50 degrees. So this is the sine of 88 degrees. What's in the parentheses? 350 cosine of 50 degrees. So let me try to solve for T2. So T sub 2 is equal to 350 cosine 50 degrees over the sine of 88 degrees. And that is my tension. Okay, good. Now let's just use R1, I guess. So let me plug back into R1. So I have T2 which is 350 cosine 50 degrees over sine 88 degrees times cosine of 38 degrees minus T1 okay, why are you stopping? Okay, it's back. Minus T1 cosine 50 degrees is 0. So let me just cancel out the cosine of 50 degrees. So I have that T1 is equal to, oh, why did that become 35? That was a 350. That somehow got rid of the 0. And so this is equal to, getting rid of the cosine of 50s, 350 cosine of 38 degrees over the sine of 88 degrees. So that's the magnitude of T1. So now let me write down their vectors. And so T1 is, maybe I'll write it as a component. So this is going to, okay. So this is T1 times T1. So it's a minus cosine of 50 times T1. Okay, so let's write this as follows. So I can just factor out. Actually, these all are just T1s. Okay, so this is going to equal, so T1 is a minus okay, so let's factor this out. So T1 is minus this amount times cosine of 50 I vector plus this amount times sine of 50 degrees J. And so that's your vector representation. Okay, good. Finally able to move it. Let's look at T2. The vector T2. So the vector T2 is just T2, which was this, 350 cosine. So 350 cosine of 50 degrees over sine of 88 degrees times cosine of 38 degrees in the I direction plus sine of 38 degrees in the J direction. And that's your answer. So those are the vectors T1 and T2. Okay, good. So that finishes off section 12.2. And actually, that's it for today. Okay, so stop recording there. Okay. As everything is frozen, stop recording. Do you want to stop? Yes. Okay. Yes. Stop.